Sandeep, start.
Okay, sir. Good evening, everyone. Uh, my project is using computer vision in determining pre-stress on a cantilever beam. This is the overview of the presentation. We are going to talk about goal, analytical approach, experimental approach, and a few details of experimental approach. Goal, as it is suggested by the title, it is goal is to determine the pre-stress on a cantilever using computer vision. Pre-stress is modeled as a constant axial load P on a cantilever beam. I'm going to explain some of the keywords. Is computer vision. Computer vision deals with how computers can gain high-level vision like humans. When we see a picture, we can immediately determine what the picture is all about, what are the parts of it, and what action is going on. But such a perception is difficult for computers, and computer vision tries to give such a high-level vision to computers. Pre-stress. Pre-stress is the introduction of internal stresses to improve the strength of component against the loads that are going to be applied on the specimen. For suppose concrete is strong against compression, but it is weak in tensile loads. So we use steel tendons like this while casting the concrete beam. We pre-stress the tendon and cast the concrete beam so that after it is completely solidifies, tendon is always in a state of tension and a concrete beam is always in a state of compression. This is the pre-stress. So when we apply axial load on it, concrete will still be in a compression state, but will be in a lesser compression state, which gives it a better tensile strength performance. And these are some other examples where pre-stressing is used. Analytical approach. Equation of motion for the free vibrations is given here. We can solve it for the exact solution and we get the natural frequency response as this expression. Here W is a deflection in transient direction. Beta is a parameter that comes up in the solution process, and omega is a natural frequency of the corresponding mode. When the axial load is applied and if we also consider internal damping, I used a wide Kelvin viscoelastic model to model the internal damping. We will get the equation of motion like this. Now we don't have to solve this complicated equation for an exact solution. Just by taking Fourier transform, we can get some insight into the equation. So now experimental approach. Our idea is to take video of response of cantilever beam with varying axial load and somehow correlate it with the axial force applied. Now for that we need to extract data from the video and then process it, and we need to get the axial load from that. So I'm going to extract natural frequencies from the video as they are easy to extract and they vary with axial load. So how to measure natural frequencies? First step is we need to track a point. We need to find the displacement of a point over time, and then we will take Fourier transform. There we can clearly see the most dominant frequency. First step is tracking a point. This is the process how I track the point. First, I use an edge detection algorithm, and then we choose a point of interest and a local interval around it, and then we calculate the centroid of the interval in each frame, and by position the centroid is considered as a displacement of that point. Here, tracking a point. First step is to get edges detected. I'm using a canny edge detection algorithm. This is an example of how an image might look like once edges are extracted. This is how canny edge detection works. First, it applies a noise reduction, which is a Gaussian filter, and then a gradient is calculated using a Sobel's operator. It calculates the magnitude and direction of gradient, and then this gradient, after applying this gradient operator, we get the edges, but the edges are very thick because of a noise reduction we have done. And in order to thin out those edges, we use a technique called non-maximum suppression. It reduces the edge thickness to 1 pixel, and then we use 2 thresholds to identify weak and strong edges, and then we consider all the weak edges, and depending on their position on the image, we decide whether they can be kept or discarded. These are the 5 steps involved in canny edge detection. Now I have also implemented another edge detection model, which is Laplacian edge detection. This works by using the second derivative. This is also called based on zero crossings of second derivative. Second derivative is calculated at all points in the image by convolving the image with a difference of Gaussian mask. Now zero crossings, wherever the second derivative is changing signs, is detected. And now these zero crossings are also validated by checking the first derivative value at that point. This is the process of Laplacian edge detection. Now I'm using canny edge detection as it works more quickly. Now we need to choose a point of interest and a local interval around the point. For example, this is a frame from one of the videos that I have taken. Here point P is tracked and a local interval of interval width 25 pixels and height 75 pixels is being tracked. Now standard of the interval can be found from this expression. We have all know this. And this value is saved for each frame and then plotted against the number of frames. Number of frames is a scale version of time, since we know the frames per second. Then we can use Fourier FFT or any kind of Fourier transform to find the frequency response and and we can easily get the dominant frequency. Now this is the experimental setup. First, I did an experiment for free vibrations. This is the camera parameters. Frame rate of camera is 120 fps. Length of cantilever beam for this experiment was 25 centimeters. Width is 2.7 centimeters and thickness is 1 mm. These are the results I have got. This is the Y position of the pixels. A point here is being tracked here. Y position is this one, and after applying FFT, we get this frequency response. Now, I have calculated natural frequency is observed to be 9 Hz from the above experiment. Now, for free vibrations, I have also developed the natural frequency expression. So by using this natural frequency, I have calculated property. Calculate specific modulus, which is Young's modulus divided by density. It comes out to be 12 into 10 power 6. The typical value of specific modulus for steel is 22 into 10 power 6. There is some error in the final output. So another experiment was done by Rohit in his lab with a better camera. This is performed by a camera at using a video taken at 960 fps. This point P is being tracked, and we have got a response like this. This response seems much more smoother, and frequency response is also not very noisy because of high fps of the camera. Here, this is another experiment. This is an experiment with axial load. Here, as you can see, I attached a hook kind of structure to the cantilever beam, and I used a thread to apply the axial force. For this experiment, length of beam is kept 30 centimeters and axial load of 2.5 newtons is applied at the free end. Yeah, this is how the load is applied on the cantilever beam. This is the cantilever beam. This is the thread, and it goes around a pulley-like structure here, and there is a ball hung to it. And gradually we increase the load, and got different responses. Now, for the above experiment, these are the results I have got. And then I have performed a set of experiments. In total, 27 experiments were done with varying axial loads, starting from 360 gram force to 3,690 gram force. Axial load is not exactly calculated because I don't have an exact weight measuring device. So what I have done is I poured water into the container shown here. I have a measuring cup which measures 180 ml at a time. So I kept pouring 180 ml at a time, which increases 180 grams weight. Now, these are results for some of the experiments. This is for axial load 990 gram force. This is for 1350 and so on. There are some inconsistencies like frame skips and these are a few more. For all the experiments, 750 frames are analyzed, and these are the camera specifications: 120 fps and resolution is 720 into 1280. Now, frequency response for the above experiments are shown here. Uh, in this graph, I have shown a total of 16 frequency responses for 16 different experiments. We can easily see that as the load increases, the frequency of a first mode of vibration is increasing gradually. Now, these are experiments. I have done a total of 27 experiments. This is starting from 360 gram force to all the way up to 3690 gram force. And I have listed the natural frequency of first mode in this table. There are some inconsistencies in this data set. We can see that for 630 and 720 gram force, natural frequency came out to be the same value, 9.36. And for also for 900 and 990, it came out to be the same value. Here also for two other axial loads, it came out to be the same value. This might be due to the friction in the pulley arrangement. Until here, increment in axial load is 90 grams per experiment. Maybe 90 grams was not enough to completely overcome the friction. So from this point onwards, I have started increasing the load by 180 grams at a time. So from 16th experiment onwards. So from that point onwards, frequencies were not the same. Duplicate frequencies did not occur. And also there is another kind of inconsistency which goes against our intuition. We know that as the actual force increase, natural frequency should increase. But here for 810 actual for 810 gram force actual load, we got 10.56 hertz, and for 900 we got 10.32. It seems for the experiment 6, data collected was erroneous for some experimental errors. Because of some experimental errors, because we can see that increase in natural frequency in each experiment is here about 0.4, here about 0.3, like that. But from 9.36 to 10.56, there is a huge increase, which is so I think experiment number 6 was the result taken from experimental number 6 is not valid. Also, this is the graph I have plotted for all the axial loads versus natural frequency. Now, inconsistent results might be due to friction in the pulley arrangement and due to air currents doors were left open because much more lighting is necessary for recording at high frames per second. And due to camera errors like frame skips and lost focus as well. Sometimes while it cantilever beam was vibrating, camera directly starts autofocusing and it loses focus. Because of that, edge detection was coming out to be erroneous, which might contribute to some error. Also due to limited frame rate. Now, last part is correlation of frequency with road. All these data we have collected, we need to somehow correlate the natural frequency that we got from the experiment to the actual load which is applied. So I decided to go with building an artificial neural network. I built a simple artificial neural network, and now a total data set is split into two parts. 22 data points are used for training and 5 are used for testing. Now, what is an artificial neural network? It is an interconnected group of nodes inspired from the brain cells. This is a neuron. It contains dendrites which takes inputs from other neurons. It processes the information and sends the output to other neurons. The same way, an artificial neuron also takes an input from different sources. It performs some calculations, gives one output, and this one output is sent to different other neurons as well. So this is how the output of a neuron that we build is calculated. It is basically a weighted sum of all the inputs, which is passed through a function called activation function. Now, activation function is included in order to add non-linearity to the neural network. If the activation function is not there, the whole neural network can be represented as linear equations, as all we have doing is weighted summations. There are different activation functions available. The one I am using is a hyperbolic tan function. This is the activation function that I have used. And now next step is to, after designing the network, we need to train the network with the data. For training the network, what we do is we give the input, we we calculate the output that the network is giving, and then we find the error by comparing the output with the known value. And according to this error, or also called loss, weights are adjusted so that the loss gets reduced for the next iteration. Now, weights are adjusted according to this formula. E is the error function, and wij is one of the weights. The new weight is calculated by this expression, and here alpha is called the learning rate. We need to keep the learning rate low so that all the training data has some influence over the final neural network. Now, this is the network that I have chosen. There are 3 layers: input layer, hidden layer, and output layer. One node in the input layer, because we are only giving natural frequency as the input, and we are getting actual load as the output. I kept 1500 nodes in the hidden layer, and now number of epochs is how many times we retrain the neural network. So I'm training the same neural network with the 22 data points I have these many times, and learning rate is kept to be this value. We need to keep the learning rate low when we are training it so many times, because if the learning rate is high, only the last few training data has the most influence on the neural network, which gives erroneous predictions. So this is the setting of the neural network that I have used, and for that this is a comparison between actual values. For the test data set, actual values are represented with the blue line, and predicted values using this neural network is depicted with the orange line. And now this whole neural network can be thought of as a function because we're only giving one input and getting one output. So I decided to plot that function. This is the curve that I'm getting, where green points are data points that are collected from the experiment. I have also tried. Yeah, these are the predictions that the neural network are giving. For this frequency, this is the actual load, while the predicted load is this one. I have also tried with a few other presets for the neural network. This is one of them, where the configuration was different. Number of nodes in the hidden layer were only kept to 1000 here. The average error came out to be higher than the previous case. Also, I have tried with various learning rates. This is another learning rate, and also another configuration. Here I have kept two hidden layers with one with nodes 1000 and one with 100. And as far as I have tested, the one that is giving best results is this one with 1500 hidden layered nodes. Yeah, and accuracy and possible improvements. Prediction accuracy can be improved by using large quantities of data points. We have collected so far only 22 data points, which are very less compared to what are actually used, what are general compared to the quantity of data that is used in machine learning in general. And we are only using natural frequency of first mode up until now. Using natural frequency of second mode as well along with the first mode can significantly improve the accuracy. And this method can also be extended to cantilever beams of different lengths and cross sections and materials. We need to do much more number of experiments and collect the data for that. In such cases, we also need to provide the geometry and material properties as inputs. So that's all. Thank you. Now, if there are any questions, you can ask.
Sandeep,